everyone, and welcome to Groundwater Talk Live. I am Tom Ballard, the Groundwater guy here, and today we're going to discuss the Langelier Saturation Index, or LSI for short, and does it really do the trick for assess corrosion and scaling potential in wells? And so we're gonna cover that today, and it's an often misunderstood index, and so we'll kind of go through what that is. I did a show. Oh, towards the beginning of the year at this point. So it's been a number of months ago on corrosion, where we touched on the LSI, but I wanted to go over it in a little more detail because it is one of those things that is misunderstood and people don't really know what it is. So I wanted to talk about it and its actual usefulness and how to basically interpret the data from this and some of the caveats. So. But before we do that, one of the things I like to ask people to do is like, comment, share. It really helps the algorithm and helps us get subscribers and reach out to more people. I've had a number of people contact me that said the information on here is pretty useful, and so I'm trying to get the word out. So every time you like and share, that helps. Comments are great. I answer all comments. So if you want to leave a comment, if you have a question or ideas for future shows, just let me know, and I appreciate that. All right, so let's dive in a little bit and talk about the Langelier Saturation Index, the LSI. It's one of a number of measures. It's a calculated measure, not a direct measurement, so you can't put a probe down a well and actually measure for LSI. There is an R index, the aggressive index, or similar types of things, but probably the LSI is the one that's most frequently used. So let's dive into that and kind of explain what it is first, how we use it, and then some of the caveats, and so you know how useful it is and really how to interpret the data. All right, so the Langelier Saturation Index is a calculated index which predicts the scaling of water based on the calcium carbonate equilibrium value. So it's really looking at calcium carbonate scaling in wells, and it does a number of things. It looks at the potential if your water is oversaturated with calcium carbonate or calcium. We use we'll go into that in just a minute here, but if it's oversaturated in calcium carbonate, then you have potential for scaling and plugging of the wells. If it's undersaturated, the theory with the LSI goes is you have corrosion potential because you don't have that calcium carbonate protective coating on the wells, and corrosion can basically start in bare iron, and so it's supposedly a measure of that. Doesn't quite really work real well for corrosion, but for scaling definitely is good. And gives you a good measure, at least for calcium carbonate scaling conditions in a well, so you know. And that's really one of the most common types of incrustations we see in wells is calcium carbonate. So it is good for that. The components of the LSI calculation, and it has 5 components here. And once again, what you're doing is you're taking these components and you're really looking at the saturation for calcium carbonate in the well. Obviously, if it's oversaturated, then it can come out of solution and you can start to develop severe scaling problems. So we're going to look at a number of these things. pH, of course, is going to control precipitation. So low pH acidic, high pH is alkaline, and so the actual pH levels enter in here, and that's really one of the most important parts of the LSI calculation. And temperature enters in because chemical reactions at different temperatures, of course, it's going to vary according to temperature. Total dissolved solids enters in here. Calcium hardness, so hardness as calculated as calcium carbonate, and alkalinity calculated as calcium carbonate. There is a non-carbonate hardness. You want to look at carbonate hardness for this calculation. And there is a formula for this. There's also a lot of online calculators you can do, but in my mind, the easiest way is to send a sample off to the lab. Now, The caveat with sending a sample to the lab is the temperature is obviously going to change from what you took the temperature at. You know, even if you throw it on ice, it may be colder than what you collected the temperature at. So the temperature is going to change a little bit. That's not the huge variable in LSI, but it can change the numbers a little bit. You know, whether the pH degrades over time, you know, things come out of saturation, you get some degassing, that can cause things to get a little more acidic. So sending it to the lab definitely has a few caveats. Whereas if you do all these measurements in the field and then you calculate it, then it might be a little more accurate, but I find just sending the sample to the lab is the easiest way to do this. But for the sake of completeness here, you can see that really what the LSI is the pH you measure versus the saturated pH. And that's saturation in calcite or calcium carbonate. So the pHs is calculated at and these are the parts of the formula here: 9.3 plus A plus B minus C plus D. A is your TDS calculation, so that's where TDS comes into play. The B is actually your temperature calculation. C is your calcium as calcium carbonate. And then D is your alkalinity as calcium carbonate. So that is the formula for actually calculating saturated pH. And then what you do is you subtract that from the actual pH, and then you get a number. And it's going to be positive or negative, and within range. Usually -2 to +2 is generally the range that LSI comes down at, and those numbers are going to give you implications for potential corrosion or mineral scaling. All right, so that's the calculation. If you really want to do that, I much prefer to have the lab do it and instead of running these numbers. But there are online calculators, like I say. If you want to calculate it for yourself, check the lab. That's great too. So you can just Google LSI calculator or Langelier Saturation Index calculator, and you can find a number of them out there. A lot of them are actually a lot of the calculators out there are from like pool companies and stuff, where the LSI is important for maintaining pool clarity and that type of thing. So they look at that pretty seriously because water hardness is a big deal when it comes to that. For wells, it is a big deal because the calcium carbonate scaling can create plugging in the wells and plug things up over time and degrade well performance. So we want to pay attention to that. All right, so interpreting the LSI, if the actual pH of the water is below the calculated PHS, saturated pH, then the LSI is negative, and that indicates the water will dissolve calcium carbonate and that it will be corrosive, particularly if dissolved oxygen is present. Now, when we talk about the water's, and sometimes you'll hear the term aggressive, that if the LSI is negative, that the water is aggressive. And what that means really is not necessarily corrosion per se, but the fact that you don't have a protective coating, and people consider the calcium carbonate, a little sheen of that on there to be protective of the bare steel. You're not going to get that if your LSI is significantly negative. So that's really where the corrosion comes in. It's aggressive. It means you're not getting calcium carbonate precipitating out and protecting the bare steel. So negative LSI means you're undersaturated in calcium carbonate, so the water will dissolve the calcium carbonate and you will not get calcium carbonate deposition in your well. If the actual pH of the water is higher than the calculated PHS, the LSI is positive, indicating that calcium carbonate incrustations scaling will occur. So your water is oversaturated with calcium carbonate, so it will start to precipitate out, and this is where you can develop significant mineral incrustations that can create plugging in the wells. So a positive LSI is something you definitely want to pay attention to because that's where you're going to get potential scaling. There's other chemistry we can run to kind of confirm that, but the LSI will give you an indication of that potential trouble. So if you have a positive LSI for a long time, you're probably going to get calcium carbonate plugging going on in your well with the development of the mineral incrustations that are going to plug up your screen. So that can help you planning your well rehabilitation. Okay, so in summary, negative LSI equals corrosion potential, kind of. Positive LSI means mineral incrustation potential, and that's mainly going to be calcium carbonate incrustations. Now, if you have water that's oversaturated in calcium carbonate, you can get other things too. So there may be other mineral incrustation potential with a positive LSI, but it's mainly looking at calcium carbonate, which, as I mentioned, is the most common form of mineral incrustation in wells. Iron oxide, iron and manganese oxides are pretty common as well, and you know there's other ways we can look at that. The LSI is probably not the best way to look at iron and manganese incrustations and deposits. A lot of those are going to be tied to biological activity in the well too. I'd say that most iron and manganese, just as an aside here, most iron and manganese deposits in wells have at least some biogenic origin to them. So you got to look at some other things that are going on. So the LSI, not terribly helpful in looking at iron oxide and manganese oxide incrustations in the well. Okay, so if the LSI is 0, the water is undersaturated with respect to calcium carbonate, but it's just at the saturation point. So environments can vary in the well. The pump is on, the pump is off. So you're going to get some variability. So if you're just at the saturation level, you might still have the potential for scaling with calcium carbonate because it can flip around a little bit. And once again, this is a calculated index, so variations in the pH, the calcium content and stuff can cause variations in your LSI. So undersaturated water has a tendency to remove existing calcium carbonate protective coatings in the distribution system and the well, but we're right at the saturation level. So you're starting to move into the saturation level when you get to 0. So it's kind of right there. You'll hear this water called balanced water. But in a well, like I say, there's enough variability with water coming in from the aquifer that it's very hard to maintain an LSI of 0 and maintain balanced water. You might be able to do that in a pool. You might be able to do that in a distribution system, but in a well, in actual practice, that's going to be very difficult to do. Once again, with the LSI at 0, the water is considered to be neutral, so it's going to be neither scale forming nor scale removing, and that's the balanced water that you'll hear termed. If the LSI is greater than 0, then it's going to be a positive LSI, and the water is going to be supersaturated with respect to calcium carbonate, and scale forming may occur in the distribution system and well. So we're looking at this in a little bit different way. I know I kind of explained this, but I'm kind of going through and kind of putting it in terms of the actual LSI numbers and kind of looking at it in a little bit different way. And then this is our LSI scale here. So if you go from -2 to -5, you have the potential for serious corrosion. Now, this is based on the assumption that removing calcium carbonate, scaling, a small amount of scaling, is not protective for the steel in the well. So you'll see these scales online, and I actually pulled this from somewhere. In actual practice, corrosion is a complex topic, and just removing the calcium carbonate is calcium carbonate scaling can provide some degree of protection. I'm not certainly not denying that, but it's not the primary factor in corrosion. So once again, using LSI for as your sole measure to look at corrosion, probably not the best tool for that. For scaling, yes. So 0.5 to 0, slightly corrosive but non-scale forming at 0. You're balanced, but pitting corrosion is possible. 0 to 0.5, slightly scale forming, and might be slightly, you might get that pitting corrosion going on. And then 0.5 to 2, it's scale forming but non-corrosive. So this is basically your scale, how to interpret the your LSI numbers. And like I say, LSI is going to range from -2 to +2, and that kind of shows you where you are in this spectrum. In actuality, corrosive tendencies may be exhibited by water containing high concentrations of sulfite, chloride, iron in the water can also indicate corrosion going on. You can have microbial induced corrosion in your well, which is a fairly common thing. LSI is not going to measure that at all, so LSI really does fall well short in calculating corrosion. pH is a better predictor of corrosivity than LSI, so an acid pH is really going to indicate a corrosive environment. ORP, which we're actually going to talk about in next week's Groundwater Talk Live, is also useful there too, because if you have an oxidizing environment, that can indicate the potential for corrosion as well. So, but it gets a little more complicated than that. Once again, microbial induced corrosion is a big thing in wells, and pH can kind of get at that a little bit because for instance, if you have sulfur-reducing bacteria in your well, they're going to produce hydrogen sulfide, which is going to create acid conditions in the well, so your pH is going to be lowered. So the pH is going to be an indirect measurement of maybe sulfate-reducing bacteria, although you don't want to rely on any one particular measure in and of itself. So all these tools that we have, all these measurements we do, we want to do a number of them and look at them in total to really kind of confirm what our conclusions are. All right, LSI is a reasonable predictor of calcium carbonate scale formation, however. So it does tell you if you're oversaturated with regard to calcium carbonate, and is a pretty good predictor of the potential for forming calcium carbonate scale in your well and the plugging. So, but once again, will not predict iron oxides, manganese oxides, those types of things. And so usually the chemistry in your well is complex enough that the things are going to vary a little bit, and you're going to have multiple things going on. I mean, we can see calcium carbonate scaling in a well and see it colored a nice orange color from iron oxide being mixed in. So there's multiple chemical things going on in your well, and that's why you really got to look at multiple parameters. When we do our well health check, we're looking at a whole range of both chemical and biological parameters as well as physical parameters to really assess everything that's going on. The LSI is one of those tools that we use, and but it's just one of the tools. You really got to look at it in light of some other things. And I think we've shown here that the corrosivity is not really well measured by LSI, but calcium carbonate scale formation really is. So LSI is a useful tool as long as you understand what it is and that you use it properly and look at all those other things that you have, your other tools at your disposal as well. Now, I talked about some other indexes that kind of do the same thing as the LSI. One of those is the Risner Saturation Index, or Risner Index for short. RSI is what it's called. So you got LSI, RSI, and the other one is the aggressive index that I'm not going to talk about here, or AI. So the Risner index predicts the tendency for scaling and corrosion, just like the LSI. It's calculated a little bit differently. It is widely used, although the LSI is probably the most commonly used one. But the way the Risner scale works is the water's corrosive in the index is higher than 7. So in the case of the Risner index, you're kind of flipped, is positive, higher than 7 is going to be corrosive, and lower than 7 is the potential for incrustations to develop. So 7 is considered balanced or neutral with the Risner index, so it kind of follows the pH scale, other than the fact that it's flipped. So 7 is neutral Risner index. High above 7 is corrosive, and below 7 is potential for incrustation. So that's the other one. And the AI, the aggressive index, you can look that up if you're really interested. But I don't see that used as much. I do see it pop up occasionally, but generally it's going to be the LSI. I see some people report both the LSI and the RSI, and occasionally see the aggressive index pop up as well. All right, so the challenge of indexes here. Wells are dynamic systems. You're going to have the pump cycling on and off. That can change your chemistry right there. It can oxygenate the water. You can have, as water flows in, you can see some chemistry changes. And over time, you can see some chemistry changes as you develop mineral incrustations in the well. You can, and enough calcium carbonate there, you can start to get degassing in your calcium carbonate, which will release carbon dioxide, which will actually acidify the well, and now you're lowering the pH, which is going to push your LSI down into the negative range. So these are factors that the more calcium carbonate scale you have in the well, the more potential you have for degassing, carbon dioxide formation, which will then lower your LSI and doesn't indicate what's going on at all. So that's a caution there. As I mentioned, biological activity, biofilm development in the well, bacteria, especially sulfate-reducing bacteria, or SRBs, will produce hydrogen sulfide gas, which will acidify the well, and that'll push your pH down as well and change your LSI calculation. So these are some caveats that you need to be aware of. If you have strong SRB development in your well, then the LSI calculation is probably going to be off, because the pH part of the calculation, which is, as you saw earlier, is a huge part of the LSI calculation, is going to be off, and so your LSI is going to be off. So keep in mind that as a calculated index, there's 5 factors that go into the LSI calculation. If any of those change due to the dynamic part of the well system, then your LSI may not be quite as reliable. So that's why I say use it as a tool to give you an indication, but look at the other parameters that like I say, during the well health check process, we go through and we have the lab calculate all these different parameters, and we look at them all together in sum total, and that really helps us make a determination of what's actually going on down there. Obviously, if you have a well video, you can kind of see things too, and so that's always great if you have that. And there's some other tools, but the chemistry and the biology analysis is really going to tell you a lot. But you don't want to rely on just one number. You want to look at everything in total, because you may miss a problem that needs to be addressed during a during well rehabilitation. And so these are important factors. So just keep in mind that wells are dynamic systems and things can change over time. So you take samples, you run an LSI. That's going to be a data point at a point in time, and that can change a little bit and vary. So you may have a 0 LSI now and a positive LSI the next time you take it, and you go, what happened? And it's just kind of, it's the time you took the sample. The pump may have been on and or you just turn the pump on, and so there's a little bit of dynamic conditions going on there that can affect your results. So I can't caution you enough to look at multiple parameters when you're really trying to assess the health of your well. All right, so that is our show today. A little shorter than normal, but I wanted to cover this. We're going to cover some of the other well health check parameters that we commonly see that might be a little misunderstood out there. Next week, we're going to talk about oxidation reduction potential and some of the misunderstandings with that and how that's used. And so we'll cover that as well, and just so you get a better understanding of what some of these tools are, how we can effectively use them, and really what some of the limitations are, because everything has a limitation, and we need to understand what those are as we interpret the data. All right. Thank you very much for attending the show today. Don't forget to like, comment, and share. If you like this content, we got more. We stream live into the Groundwater Guy YouTube channel and also into LinkedIn. And so you can find us there. All the past shows are on the Groundwater Guy YouTube channel. So you can look us up there and check out those past shows. A lot of interesting stuff there. We got a lot of shows up there. So like, comment, share. Let me know what you think. Thanks for watching. Don't forget to subscribe to the Groundwater Guy YouTube channel, and we will see you next week.